Hello, everybody. Welcome to today's webinar, Outside the Box Options to Advance Multifamily Building Efficiency. Today's event is the sixth and final webinar as part of the Building Energy Codes Program Seminar Series, sponsored by the U.S. Department of Energy as a follow-up to this year's National Energy Codes Conference. And now, without further ado, I would like to introduce Kevin Rose from the Northwest Energy Efficiency Alliance, who will be moderating today's webinar. Kevin, take it away.
Yeah, thank you, Richard. I want to quickly frame up today's conversation with just a single slide here and talk about multifamily, why it matters. I suspect that a lot of y'all who are on the call today already think it matters, and that's why you're here. But just to provide a quick snapshot, if you look at that gray line, which shows buildings under construction, you'll see that multifamily more is being built now than ever before in the past. I think in June of this year, we hit a new record high for multifamily buildings under construction across the country. So while there are lots of reasons why multifamily makes sense from an economics perspective, based on a lot of what you hear about availability and costs of materials and housing crises and affordability crises, the data backs that up as well. And with more multifamily being built than ever, more people involved in the design and construction and inspection of multifamily than ever, there's unique challenges to multifamily. And so we're here to talk about some solutions to those unique situations here today. Next slide, please. So quick agenda for today. We're closing out the intro now. We're going to go over to Rob Aldrich from Stephen Winters Associate, and he's going to give us a little bit about heat pump water heaters in multifamily buildings, focusing on integrated units and the unique challenges there. After some questions with that, we're going to go over to Dwayne Johnlin from the City of Seattle, and he's going to give us a little bit of a case study and some structural changes, an innovation to the structure of the code itself in Washington related to low-rise multifamily. And I'll provide a little cameo at the end of his presentation as well. After some more Q&A, we'll close it out and call it a day. Next slide, please. All right, so now I want to pass it over to Rob to start with our first presentation.
Thanks. My name is Rob Aldrich. I'm an engineer with Stephen Winters Associates. I'm in our Connecticut office. We work on the East Coast, Northeast, Mid-Atlantic, offices in Boston, Connecticut, New York, and DC. And we focus on better buildings in lots of different ways. We're about 140 people all told. We focus on efficiency, sustainability, health and resilience, accessibility. I'm here to talk about a very specific topic, and that's heat pump water heaters. And as Kevin said, integrated tank heat pump water heaters. This is the type of product I'm talking about. It's a tank of water with a heat pump on top of that tank of water, which extracts heat usually from the surrounding air and moves that heat into the water. The first kind of evaluation project I worked on was here in Connecticut back in 2001. And these have kind of come and gone over the years, this technology. There were some improvements needed with the products that we evaluated back in 2001, but to a large degree, those improvements have been made. Products now are a lot better, a lot more reliable than they used to be. I do want to say my experience is really mostly in the Northeast, New York and New England, in colder climates, climate zones 4, 5, and 6. I'm going to try to generalize for the whole country, but do keep in mind that my perspective is a little bit tempered by challenges in cold climates. So I want to just put that out there up front. So the one thing I see a lot of screw ups with these systems applied in multifamily buildings. Very often in the Northeast, we see them installed in the basements of single family homes, and they usually work pretty well. I'm going to say this again because this is what I think people miss, is these devices, they extract heat from the surrounding air, or sometimes you can duct the air to them and from them, and they move that heat into the water. That means that they cool and dehumidify the surrounding air. Sometimes that's great, sometimes that's not so great. I also want to mention that most products do have backup resistance heating elements that will kick in when the heat pump cannot keep up with capacity, with demand, or when the surrounding air, the incoming air, is just too cold for them to operate. I'm gonna hopefully not beating a dead horse, but integrated heat pumps remove heat from the incoming air and transfer that heat to the water. That means the air coming out is about 20 degrees cooler. So we have somewhere around 200 CFM of, if the incoming air is 70 degrees, we have 200 CFM of 50-ish degree air coming out. One analogy that I've been told by my colleagues kind of really hit home for them, it's like running a small air conditioner 5 to 6 hours a day. If you have a heat pump water heater in the basement of your home, it's like running a small window AC 5 hours a day. It's a significant amount of cooling if the heat pump is doing all the work. And that is the factor that I see people miss, and they misapply this technology. So again, these can work very well. They can be very efficient. The keys to the efficiency, most of it has to do with limiting the use of that electric resistance. As I said, there are backup resistance elements in most of the tanks. You can do that in several ways. One is a bigger tank, so you have more hot water to use before the resistance has to kick in. You can keep the water hotter as long as you install, anti-scald valves so you don't scald people. You have, if you have more hotter water, you can go longer without kicking in electric resistance. And certainly warmer intake air helps. The minimum for these to operate with R134A, which is what most of the ones I'm familiar with still use 134A. In the 40s, the heat pumps stop working efficiently in the 40s. I think below 40, you're not going to get anything at all from these systems. And warmer is better. Certainly the warmer the intake air, the more efficient these things are. And of course, I want to say another way to reduce energy use is to use less hot water. And it also makes these more efficient. If you use 150 gallons of hot water a day in a single family home, this is probably not going to keep up. If you use 30 or 40, there's a good chance the heat pump could keep up with the entirety of that load. So good applications. A lot of basements in the Northeast of single family homes. I know a lot of people put them in garages in non-freezing climates. I get very nervous when people put them in garages in upstate New York, but certainly a lot of the country, garages are certainly a practical application. If you don't have a basement, you don't have a garage, if you're in an apartment, then what do you do? And this is just a very simple, example of an apartment plan. Very often, too often, I see people try to put them in closets in multifamily buildings. And this is almost always a bad idea in my experience. This is a photo that one of my colleagues sent me for a project he was working on in New York State. I didn't work on this building. This is maybe like 10 years old. But man, there's a lot that's going wrong here. This heat pump water heater, none of the clearances are being met here. I don't think you can get the cover off this electric panel. The drain pan is crushed. And these heat pumps, they extract heat from the surrounding air and move that heat into the water. If you put it in a tiny closet, there's just not enough heat in this air to provide heat for that water. You'll turn this on, and within minutes, this closet's going to go down in the 40s Fahrenheit, and the heat pump's just going to stop operating. You can see what happened here. This closet got very, very cold. Somebody had the brilliant idea of running an extension cord and plugging in an electric resistance heat to keep this closet warmer. That defeats the entire purpose. And this is actually an exterior door. So this is a closet in a multi-family building. This is an exterior door. So somebody had the brilliant idea of cutting louvers in the exterior door to let the nice 20 degree January air into this closet. That was a disaster. And this developer or not the developer, the property manager actually didn't want to put these in. He was saying, God, the utilities begged me to put these in. They were throwing money at me. They paid me more money than it cost to put these in. So I finally put them in. It was a train wreck, had to rip them all out, put in electric resistance. I'm never using heat pump water heaters again. And that's not a good example. We want to minimize these kind of applications. We've worked with these people since then. We've talked them down from the never again heat pump water heaters, but it's a very bad application. So one solution, quote, solution I've heard proposed is just, put louver doors on the closet door. I have not seen this work personally. I still see that closet getting down to 50 degrees or below where the heat pumps cannot operate efficiently. This is 200 CFM, and you need a way to really actively move air in and out of this closet. In my experience, just passive airflow, passive convection through a louver door doesn't cut it. You still get very cold closet temperatures, and the heat pumps don't work efficiently, if at all. The other thing that louver doors, the issue they raise is sound. These things are not silent. They're fairly loud. I think all the ones I'm familiar with are in the 50 decibel range, maybe even higher. They're getting better. They're getting quieter, which is great. And 50 decibels is not hugely loud, but if it's right next to your bedroom and you're trying to sleep, it may be too loud. This picture is taken with the louver doors open in an apartment. And you can see there's a heat pump water heater on the left. There's a air handler on the right. I won't comment on ducting for the air handler. But with the louver doors closed, the sound pressure in the living space on the other side of the doors was 53 decibels. And I've heard really building owners having bad luck where residents get frustrated with the noise and they switch their water heaters into resistance mode, or what they call quiet mode. So because they can watch TV and they can sleep without the noise of the water heaters providing an annoyance. So sound is definitely something to think about in multifamily buildings. So ducting. Ducting is sometimes presented as a panacea, solve all the problems related to water heaters and closets. Here, if you have the exhaust from the heat pump water heater and you exhaust that into the living space and you have a louver door that'll allow makeup air back into the closet, thermally this could work. You might get some short circuiting, but generally I think you'd probably have enough warm air coming back into the closet for the heat pump to operate efficiently. This does not solve the noise issue, and also you have about 200 CFM of 50-degree air blowing into the apartment. That may or may not cause comfort problems. If you perhaps don't have a louvered door, maybe you soundproof a closet, a gasketed door with nice, caulked tight closet, and you duct both the intake and the exhaust. Here again, thermally, you might be okay, but you're still providing 200 CFM of 50-degree air into the apartment, and you have to figure out a way to do that where it's not going to cause comfort problems. I think the sound could, you might get some sound propagation through ducts, but if you do duct it thoughtfully, you can eliminate a lot of the sound problems. And this is one of the areas which is very climate dependent. 50 CFM of, 200 CFM of 50-degree air in a Miami apartment could be great year round. In Chicago, it might be nice for a few months, and for a good part of the year, it's could be a real comfort liability. So you have to be really thoughtful about how you incorporate these into apartments. This is kind of an example of what I would say is a qualified success. This was a project in Connecticut. It was a gut renovation of an old mill building. Actually, they converted it into 80-ish apartments. Every apartment has a heat pump water heater in the closet, and you can see here one side was ducted. This is the intake to the water heater was ducted. Some flopping flex duct that could be improved here, but the exhaust came out of the water heater and into the closet. And this is a fairly large closet, but there were louvered doors that separate this closet from the rest of the apartment, and that cool air just kind of oozed into the apartment, mixed with air in the living space. And in general, it worked okay. I talked to the building manager here. I got great information from him. He said there were a few apartments, 2 or 3, where the sound and the cool air really were unacceptable to the occupants. So he had to go and switch them into resistance mode. When it got cold, and this has been occupied for a couple winters now, I think we're going into the 3rd winter. When it got cold, there were a lot more problems. There were a lot more complaints, and there were comfort complaints, and there were also performance complaints, which actually I don't quite understand. The heat pump water heaters weren't keeping up always, but there were enough complaints that he ended up switching a lot of the water heaters over into resistance mode. So for following winters, their plan is for 3 winter months to switch all of these water heaters into resistance mode. Eliminate the performance concerns, eliminate the comfort concerns. And for them, that's a success. I mean, they're still using much less electricity, much lower carbon impacts than if they were just going with resistance. In the winter, they are doing resistance. So if winter peak issues are a big concern, that's not addressed by this example. But I encourage people to think outside the box. These devices work, but they do have limitations, and you have to figure out how to kind of work with those limitations. Ducting to outdoors is something I never recommend in a cold climate, at least with the equipment we have now. In milder climates, it may be viable. So think about your climate, think about your application. One thing I think about, I see people propose here is ducting just the exhaust outdoors, which I think is just a very bad idea almost everywhere. You exhaust 200 CFM outdoors, that means you're drawing in 200 CFM from somewhere. Where is that makeup air coming from? Is it 10 degrees outside? Is it 90 degrees outside? Is it coming from the hallway, from your neighbor, up the garbage chute from the parking garage? Uncontrolled infiltration is not a good thing. So ducting to outdoors has some challenges. Check time. All right, I'm in good shape. This is an application which I don't have any firsthand experience with, but I've talked to several people who have tried this approach. In this example, you have a mechanical closet with a water heater in it, and that closet is accessed from the corridor. So right there, it has the appeal that maintenance staff can get to the equipment without going into the apartment, which is nice. If you do nice, tight, soundproofed walls around the closet, the noise won't propagate into the apartment. If you exhaust the water heater into the corridor and have a louvered door so that air can come back into the corridor for the water heater to work, this, I think, has some promise, but I have not seen any kind of real detailed results from this. You are cooling off the corridor a lot. And here again, that's something you have to think about. You're going to be adding a heat load to this corridor, and that heat load should be addressed as efficiently as possible, not with electric resistance, or else you're kind of defeating the purpose of the water heater. And here again, if you have continuous cooling, year-round cooling to your corridor in Texas versus Montana, it's very different, very different can of worms. So this is one of the, I wish I had some real data on how these systems perform. But anyways, I think it's a potentially a promising application. So central plants, I've seen several instances of people ganging several integrated tank heat pump water heaters in a central plant. And at first pass, this looks pretty nice. We have nice insulated pipes. Looks like there's nice reverse return plumbing. One of my colleagues, a couple of my colleagues were involved in this project, and they just happened to mention it to me, this approach, and to me it sounded horrible. And they were kind of baffled as why, and nobody realized why. The engineers didn't realize why, the utility didn't realize why, the plumbers didn't realize why. But what you're doing here, this is about a 25 unit building being served by these 6 water heaters. It's extracting heat from this mechanical room. So all the heat for the hot water to 25 apartments is supposed to come from the air in this mechanical room. I was very concerned that there was not enough heat in the air in this mechanical room to provide all that hot water. And one of my colleagues went to inspect this system to see how it was performing. She saw, hey, a huge electric resistance heater up in the corner. And if we go to the other corner, another big electric resistance heater. She found that both of these heaters were running for several hours a day in August when she inspected it. So 80 degrees outside, we have 2 big electric heaters running several hours a day to heat this mechanical room so the heat pumps can move that heat into the water. There's just a fundamental gap with understanding of how these work. But what you have here is a central plant electric resistance water heater that was very expensive. It may have modeled great when you plug in an energy factor of 3 into your models. Got great incentives, but it's effectively a central electric resistance plant. So think about where the heat's coming from that these heat pumps are going to use to heat the water. And it's possible to do this. You know, this was a bad example. I don't recommend it, but it's not out of the realm of possibility if you do a very, if you do a considerate, thoughtful design. Perhaps in the summer you can bring outdoor air in for 2 or 3 seasons. You want to be careful of, filtering and screening and pests and humidity and yada yada. There are things to think about if you bring outdoor air into the space, but there is certainly heat in the outdoor air in August. We shouldn't be using resistance heat to heat that air. Maybe you can have a, ductless mini split heat pump heat that space. Not nearly as good as using free heat from outdoors, but better than electric resistance. If you're using a heat pump to heat the space and then another heat pump to heat the water, as long as both COPs are above 1, you're going to be better than resistance. Maybe not tons better in some applications, but you're going to be better than resistance. So again, it's worth being careful. It's worth being thoughtful, but don't just use resistance. So a few years ago, we put together a document for Eversource, which is a utility here in New England. And it basically, here's a link here to this document. It just outlines the issues, some of the issues that I've been raising. It doesn't present any silver bullets. I don't have any silver bullets for systems that work perfectly, but it really just advises you of these issues and encourages you to really think through these issues for your particular application. So that's it for integrated tank heat pump water heaters. Just a few minutes to talk about other options. Certainly, if you have a split or monoblock system where your evaporator is outdoors, systems, people I'm sure probably have seen them. You have an outdoor unit that looks like a heat pump outdoor. It is a heat pump outdoor unit. Sometimes you have refrigerant that connects the indoor and outdoor units. Sometimes you have water lines that go outdoors, water gets heated up, goes back indoors to a storage tank. This solves the sound problem. It solves the stealing heat from indoors problem. And there are systems like this one, which uses CO2 as a refrigerant. This can operate down well below 0. This circled outdoor unit is the water heater, and the image of the tank is on the left. This is in Connecticut. It's worked great for a couple years. I'm not going to get too much into the detail of considerations for these systems because I was focusing on integrated tanks, but we've seen folks attempt to, and well, some successfully, some not successfully, scale these systems for a multifamily building. This is a project done by Tatum Engineering in Ithaca, New York. They did a great webinar. Actually, I saw an ICERTA presentation yesterday, which had some updated info. The link I have here it's on YouTube. This is a webinar they did about this project 6 months ago, but I saw some updated information on the webinar yesterday. This system is working well. I know other developers who have tried this and ran into big headaches, big hassles, like rip it out and do something entirely different level hassles. It's not a straightforward plug and play system. You have to be very careful when designing these systems. It's a lot more nuanced, and it's a lot different than just specifying a boiler and a indirect tank, for instance. But we are working on a lot of multifamily projects. This one is a hotel, which is using Mitsubishi's new CO2 system. This is up and operational. We don't have any performance data, although I'm bugging people to try and get some performance data. We have several other projects in design or nearing construction that are using central heat pump water heaters, largely with CO2. This is a project that's using water source heat pump with wastewater heat recovery, a heat pump to recover heat from wastewater. This is a big topic. I don't have any silver bullets though. This is early days, at least in cold climates, when heat pumps are intended to run all winter, provide hot water all winter. We're still figuring a lot of stuff out. So stay tuned. We hope to get data from our projects, and we're paying close attention to what others are doing. And lastly, this is a project that's under development now. This is in Massachusetts. Quite a few dwelling units, 750 or more. This developer, this is Passive House. They are using electric resistance tanks in apartments, and this is something that we kind of unfortunately keep coming back to. There are still very often projects where heat pumps are not in the cards for various reasons. First of all, there's still a lot of question marks. Even when we do recommend heat pumps install big central systems, very often there's on 100% redundant resistance because people don't trust these heat pump systems yet. Cost is obviously a huge factor, but decentralized electric resistance tanks, very well insulated tanks with low flow fixtures, with efficient appliances, insulated plumbing, smart distribution, it's not the end of the world, even though we'd like to have some more satisfying solutions that get above a COP of 1. In cold climates, we're still coming back to electric resistance quite often, but stay tuned. And I think that is it. Thank you.
All right. Thank you, Rob. We do have a big lot of questions for you, so we'll be picking and choosing, and for those questions that we don't get to, I think we can have some follow-up afterwards, so don't despair. So I wanted to touch on first, there's an early question about wanting to see discussion about a split system, which we did just talk about for a little bit. They commented, seems like a common technology that could solve the issues of integrated heat pump water heaters. Is there anything further that you want to say about split systems, Rob?
Yeah, so that picture I showed of the indoor unit, the indoor tank and the outdoor unit, that equipment cost was $5 or $6 grand, not including installation. That's pricey. If you're doing a unit by unit application, that's very pricey. I haven't seen anybody try that approach where you have a split system for each apartment. Just from a cost standpoint, it hasn't penciled out. That's the big yeah, the elephant in the room is the cost. And on the central system, if you use split systems for central systems, certainly can work. I think it just requires rigorous design, very careful design, and hopefully we all get more experience with that moving forward.
All right. The next question is regarding sound, and the question is, for the benefit of designers, what is the acceptable decibel number we should shoot for in rooms around the heat pump water heater? And they go on to say, assume that this is not an ultra quiet passive house level envelope.
I don't have a great answer for that. I've seen some kind of indoor environmental quality criteria say you don't want more than 35 decibels. That's really, really quiet. But over 50 decibels is pretty loud. Over 50 decibels, if it's near living space, if it's near a bedroom, I think could really be problematic. So I can only tell you kind of anecdotes. Like if you have a heat pump water heater in a basement of a single family home, it's kind of like if you have a basement dehumidifier. I have a basement dehumidifier in my basement on the first floor. If I pause and listen, I can tell if that basement dehumidifier is on, but it never wakes me up. It never annoys me as a sound. So in basements, I've rarely seen them provide an issue, but if they're in a closet next to a bedroom, I definitely have heard issues. I don't know what a good decibel number is, between 35 and 50, but that's a big range.
It's a starting place, but maybe more research needed for the specific application. So another question, is there a heat pump water heater that can serve both domestic water use and a hydronic space heating ducted fan coil in a small apartment?
Well, not an integrated tank, at least not if you're extracting heat from the apartment. So there are split systems, air to water heat pumps, which have an outdoor unit which extract heat from the outdoor air, and it moves that heat into an indoor tank, and then that heat and that water in the tank can be used for hydronic heating and domestic. I haven't seen them catch on at any scale, and I personally don't have enough experience to talk about them. Um, but all I can say is that there are such systems. I don't have a lot of experience with them, I'm afraid.
All right. Lots of questions and more coming in. We're definitely not going to be able to get to all of them, so I'll try and pick out some ones that several people are asking about. So Rob, you mentioned that uncontrolled infiltration is not a good thing. Do you mind elaborating on that a little bit?
Well, it's interesting. This has come up in a couple projects we're working on recently, where a heat pump water heater takes 70-degree indoor air and exhausts about 200 CFM of 50-degree air. I've talked to designers and developers, say, oh, well, that's going to cause a comfort problem in the winter, so we'll just take that 50-degree air and dump it outside. If you dump 200 CFM of air outside, you're going to be pulling in 200 CFM of air from somewhere, and doing that without knowing where that's coming from, I think is bad. And in extreme, if it's very cold out, if it's 20 degrees outside, it's a big energy liability. 200 CFM of 20-degree air is a lot bigger heating load than 200 CFM of 50-degree air. But I mean, infiltration is a whole can of worms, which we can't get into here. But we're trying to move more and more towards airtight construction with balanced heat recovery ventilation, minimizing unbalanced exhaust ventilation, and even when you have exhaust ventilation, trying to provide reasonable ways for that air to come in, makeup air to come in, that doesn't pose health impacts. I think that's all I want to say at this point, because that's a big separate topic.
Very good. Maybe a couple more questions, and then maybe we'll circle around to more of these at the end. Rob, you mentioned that you're located in the Northeast, and so you're very much biased to the systems that you've seen up there. You mentioned the EverSource guide that is relevant to their territory, which is also Northeast. Are you aware of similar resources that also are relevant to like your southern swamp climates? More similar information for folks in other parts of the country?
Well, NIA has good resources for sure. NIA has some great resources about heat pump water heaters. And when I look at them, I'd say like 90% of it plus is spot on. And then there's 10, maybe up to 10%. It's like, oof, I don't think that's good for a cold climate in the Northeast, or that's not the way we build buildings here in the Northeast. So certainly check that. I would certainly point there. I don't, it's ironic. I mean, I was at the ACEEE summer study, and there was lots of talk about heat pump water heaters. In New York and New England, utilities are trying to get these installed as fast as possible. In Florida, where they make tons of sense, people couldn't care less about installing heat pump water heaters. So it's ironic and unfortunate. There's a lot more potential and a lot fewer problems in warmer climates. But other than the NIA resources, nothing jumps to mind, I'm afraid. You might be able to answer that, Kevin, better than me.
Yeah, I realized that I failed to introduce myself at the top of the webinar, and so this will make more sense when folks know who I am. So yeah, I'm Kevin Rose. I'm with the Northwest Energy Efficiency Alliance, or NEA, which Rob just mentioned has some resources about heat pumps. I promise I did not pay Rob to plug us, but now at least folks know that that you did. So I appreciate that. I'll focus on hitting as many questions as we can here. Maybe just one more for now. And we're going to talk about, let's see, um, uh, energy recovery. Is there any requirement for energy recovery of the exhausted air? And this maybe varies by jurisdiction.
Well, I mean, if we're talking about heat pump water heaters, so I'm assuming we're talking about ducted integrated tank heat pump water heaters. And if we go to do you see, are you seeing slides at this point?
We're still on your final slide.
Oh, well, something weird happened. So I'm assuming you're talking about ducting the heat pump water heaters to outdoors, which I definitely don't recommend in a cold climate because half the year it won't work and it may impose some big infiltration and, you know, introducing very cold air into your potable water plumbing. The short answer is no. I've heard proposals about doing some funky approaches to integrating ducted heat pump water heaters in with ventilation systems. I definitely encourage people to be clever and creative about this, but I haven't seen too many approaches that are A, thermodynamically sound, and B, just practical to install and maintain. But that certainly doesn't mean that there are clever functional systems out there that make a lot of sense. So that's an unsatisfactory answer, I think, but that's all I got at this point.
You're doing great. So we're gonna switch over. There's more questions than we have time to answer, but we're gonna switch over to Dwayne. While we're changing who's hosting things over here, I'll just mention a couple other comments that came in. We were talking about resources for heat pumps. ACEEE and NBI released a report last year on heat pump water heaters and multifamily. And while we're plugging people, that report references Stephen Winter Associates work quite a bit. So that's great. So folks can maybe take a look at that. But now we're going to pivot over to Dwayne Johnlin. And Dwayne, we'll have your slides up in a moment, and you can take it away.
That sounds like a deal. Before we go on to my slides, though, I wanted to say that we're having pretty good luck in the Northwest with central heat pump water heater systems for multifamily. I would never want to put one of those integrated units in an apartment. That just sounds like a disaster in the making. But we either use those reverse cycle chiller types in a parking garage under the building, where the temperatures stay, even on very cold winter days, temperatures always stays above 40. Or we're using those CO2 based systems gang together, and which can function just fine on the roof or out in the garden, and really haven't been running into much problem there. Anyway, that's not my talk, that's his talk. I was just asked to mention for this webinar a code change that we just recently did in Washington State. And the idea, well, putting all multifamily into one energy code instead of having one code for 1 to 3 story multifamily and another code for 4 story and up. This has been, I tried to track down the earliest origins of this. I was actually able to talk with one of the people who was part of the original negotiations for the ASHRAE standard, and he couldn't remember exactly. He thought it had something to do with the height of a building for fire truck rescue. Someone else thought that maybe low-rise multifamily had a similar surface to floor area ratio to houses and therefore should use the same code. I'm thinking it might have just been a little turf battle, but right now I said 3-story. I meant to say 4-story apartment building complies with the IBC. So taller apartment buildings, and then all the other codes that go with the IBC. Whereas 1 to 3-story buildings are using the residential part of the. They use the I. Let me just go back. Sorry, I have COVID. I have an excuse. Right now, a 3-story building will comply with the IBC, whereas the IRC, the residential code, is just for houses and townhouses. And on the other hand, if you have say a development with some 3-story and some 4-story apartments, they'll all use the same building code, fire code, all that, but they will use 2 separate energy codes. Also, if you think of someone who builds a 3-story motel and a 3-story apartment right next to each other, those will use the same building code, different energy codes. This has been kind of a bizarre separation, and there's been some attempts made to move this from so that multifamily would all be in one code, but hadn't succeeded up till now. So what we did in Washington State was just to simply change the definition of what a residential building is to exclude group R2. There's that picture on the bottom is my house last winter. So we got a regular single family houses and townhouses are residential buildings, and that's it. We did make an exception for what in this part of the country we refer to as woody walk-ups. I think of them as California style apartments or garden style apartments, but those that have exterior entryways, we allowed those to choose either between the residential or the commercial provisions of if they wanted to go there. And this partly had to do with the fact that there was it looked like for those kind of apartments, the energy use would be lower, sticking with the residential code, and also that those little apartments are sometimes built by regular home builders. So any other kind of apartment building that has interior corridors used to access the apartments is considered. It would now use the commercial side of the code. So it's a very simple code change. One thing is that I wanted to say, just as a cautionary tale, that that thing with the woody walk-ups was kind of a late adjustment to our code language, and we said, okay, they can use the residential energy code requirements, but if you look in the residential energy code about heat pump water heaters, which we now require for single family, that it says it only applies to single family townhouse. So it's not even clear what happened there. If it is interpreted to say that yes, the residential code requirement for heat pump water heaters does apply, there's an exemption for dwelling units smaller than 1,000 square feet, which at least in this part of the country now would include almost all apartments are smaller than 1,000 square feet, and another for those little dinky 20-gallon or smaller units. Just to say, writing code language is always dangerous. In looking at the two, we can see that those highlighted were the more stringent values. The commercial tends to be a little bit more restrictive, not tremendously, but a bit. We also rely in both codes in Washington on our additional efficiency credit options table, where we have everybody has to do a certain number of above code things. We had one kind of point system that's gone into effect for the commercial side of the code, where you have, and each of these credits is worth a very small amount. You have to get 41 credits. Well, if you look at the top of that screen, you can get 42 credits just by right sizing your hot water distribution using the Appendix M method in the plumbing code, which is kind of an automatic here because we have fixture flow rate standards that make the Appendix M option allowable in all cases for new multifamily. And this ended up actually reducing construction costs because the pipe sizes are smaller, the insulation gets thinner, the circulating pump gets smaller. So that actually was with a single option that you get enough credits to get your 41 points. Or you could select, I have a list of things I looked at there, the ones that I put in bold, add up to 41 credits, modest amount of money. In the residential code, we have a whole different system for what these items are worth, but as a typical method of how people would achieve their 6.5 credits, that was coming up to 10 times what it costs for the credit system in the commercial code. So it started off with a lot of resistance from the home builders and other industry people who, and then eventually melted away to the point where they said, well, okay, we won't vote against it. They abstained, which was a kind of a victory. I did want to say before we go on and finish this that with all these things we're doing, that we look carefully at all the other impacts we're making as we do these changes. Make sure that people are well taken care of, and then we won't give ourselves a bad image as we move forward into this more advanced level of energy efficiency. So that's it. Just a very simple change to put all the code language for multifamily buildings into the commercial side of the energy code.
Thanks, Dwayne. As I previously mentioned, I'm going to provide a little bit of extra because Nia had the joy of being involved with this proposal, with working with Dwayne and the award-winning Washington Energy Codes group that works together to do some real impressive stuff for Washington State. Nia wanted to take a look at this when it was in the ideation stage. Dwayne laid out all the good reasons why we should be looking at this arbitrary division between residential, commercial, and maybe do something about it. And we're not the first to raise those questions in Washington, certainly. But we wanted to make sure that if we were moving low-rise multifamily from residential to commercial, that we weren't working against ourselves from the energy efficiency perspective. So Nia funded some research to answer the following research question. Would those low-rise multifamily projects consume more energy complying via the commercial code than they would the residential? So very quickly on our methodology, we modeled 2 prototypes, which represent a fair amount of the multifamily construction in Washington. Sort of probably typical in lots of the the country, sort of double loaded corridor building. And then Dwayne mentions the what we call the woody walk-up type, which I think is a smaller portion of the national percentage of multifamily, but that probably varies by local market. So those are some regionally approved prototypes that if those exact figures look unfamiliar, in the Northwest, we've been using, specific prototypes and modeling criteria for a long time, and so that's where those come from. We also had to make some key assumptions about which energy credits would be gone after, as Dwayne just finished his presentation by saying. There's, like increasingly is happening in the rest of the country, there are energy options that you need to reach a certain number of points for. Washington was on the cutting edge of that, and it's a fairly complex section of the code with respect to other states. But to simplify it, we just looked at two scenarios that were reasonably likely. One that emphasized heat pump water heater, sort of the equipment focused path, and then another path that focused more on the envelope. So we just modeled two scenarios for each of the two prototypes. So if you go to the next slide, you'll see very quickly all of our modeling inputs and assumptions, just in case folks want to revisit this after the fact. Go on to the next slide and we'll get to the outcome of this research. Again, we were looking to see if we would work against energy efficiency by moving residential low-rise multifamily into the commercial code. So the first thing we looked at was the baseline before doing anything with energy credits. And if you follow the green circles in the tables on the right of the slide, you'll see that the EUI, energy use intensity, for commercial, we found to be lower than that of residential. So early indication was that for both the double loaded corridor and the woody walk-up prototype, that the commercial looked like a pretty good option. But as Dwayne alluded to earlier in his slides, when you add the credit selections to it, the woody walk-up looks a little less like it's a slam dunk in terms of being more efficient on the commercial side. We found it to be maybe about the same in terms of EUI at the end of the day. Whereas for the double loaded corridor, where you have more common space, more opportunities to implement measures in that common space on the commercial side, we found that the EUIs were lower on the commercial side. So we'll head to the next slide. So what does all of this mean? It's a Washington-focused case study, and you heard that in our next code, which the voting for this was just approved over the past couple of weeks, we will be moving the non-woody walk-ups, if you will, to the commercial code, with the woody walk-ups given the choice of which code path they want to go for. Outside of Washington, this same matter of the arbitrary division between 3 and 4 stories exists almost everywhere, right? And different builders and developers who are forced to do something very different once you go from 3 to 4 is something that folks might locally have interest in innovating on and do something about. So if you're interested in taking a look and want to make sure that from the energy efficiency perspective, you have good information into that sort of decision making, you could maybe replicate something looking like what we did in Washington. Again, our code differs pretty significantly from the IECC, given all of our strengthening amendments and our complex options tables in particular, but you could replicate the sentiment of our analysis. So that's my last slide on this. If you advance one, you'll get my contact information. And if you advance one more slide, we'll go into Q&A. And I now have to reorient myself with the questions. Richard, did you see anything come in for Dwayne or myself while I was talking?
Just one here recently. It says, with all the concerns about sound and exhaust air temperature loads in a single family home, why are utility companies pushing for heat pump water heaters instead of tankless gas fired water heaters that would resolve the sound and EA issues, as well as gain savings by not needing to maintain the hot water temperature at the storage tank?
Okay, Dwayne, that might be to you.
Sure. Although I think it might actually be directed to our first presenter, but
Oh yeah, yeah.
uh, we're bound and determined to wring all the fossil fuel use out of our buildings over the next couple of decades, and so further use of fossil fuel for water heating is not on the table. And there are pretty easy installations for, especially for new construction, that that take care of the problems with noise and anything else you've got concerns about. Multifamily, I wouldn't do it in a little apartment, but for a single family house or a townhouse, we got lots of options to make this be part of an integrated building design.
Okay. I see a question for me. The question is, which software did we use in doing that analysis comparing the residential and commercial? That's SEAM, which is another unique to the Northwest element to our analysis. So yes, SEEM, SEAM, it was the software we used. Let's see. Looks like, Dwayne, could you mute your mic, please? We're getting some feedback. We might have one more for Rob here. Would ducting the inlet output of heat pump water heater by the refrigerator and maybe the stove within a unit to utilize that heat be a viable option? They go on to say that they've seen this attempted in manufactured housing to relatively good success.
Ah, interesting. Hey, if it works, great. In general, I say if you can find an effective way to make use of waste heat from somewhere else in the building, yeah, go for it. I'd be a little skeptical that there's enough. Refrigerators are so efficient. I'd be skeptical that there's enough waste heat coming off refrigerators these days to make a difference, but I haven't run the numbers on that, so I can't say. That was just my kind of gut. If you've seen it work pretty well, then cool. Yeah. I've seen applications where they're in a multifamily building, there may be some commercial space, there may be some restaurant space where there's a lot of heat generated from stuff. If you can take that heat and extract that heat and use it to heat your hot water, cool. Be thoughtful, be creative, but also be careful about designing such systems.
Okay, Dwayne, we have one for you. How does moving multifamily buildings to commercial code affect occupancy sensing in the units?
Occupancy sensing in units? I don't think we have any need for occupancy sensing in units or any requirement in either the residential or commercial side of the code.
Yeah, I'm not sure if the question was referring to lighting or, mechanicals related systems, and maybe this varies by jurisdiction where folks might have different code requirements.
There are things like that in that we have set up for hotel occupancies, but not for residences. And also, in regards to that last question, the cooking and refrigeration, the refrigerator running are intermittent things. You've all heard your refrigerator turn on, run for a few minutes, and turn off. And And same with the water heating. So it's not clear that they would be happening at the same time to be able to directly move heat from one to another.
All right. Well, it looks like we're at time. So Richard, I'll turn it over to you to send us home.
Yes, thank you, Kevin. On behalf of the Department of Energy, I would like to extend a big thank you to our speakers, Rob and Dwayne, and to Kevin for moderating, and to Nia for hosting today's webinar. We really appreciate you taking the time out of your busy schedules to meet with us, and thanks to all of you for participating. And as mentioned earlier, this was the 6th and final event in our seminar series. This webinar was recorded, and a link to the recording will be posted on energycodes.gov in about a week. Recordings of the previous 5 events are currently available there right now. Okay, yeah, so unless any of our speakers have anything else they'd like to add last minute, that will do it for today. Thanks again, everybody, and enjoy the rest of your day.
Thank you.
Thanks, everyone.